Preorder traversal. Preorder traversal is a type of depth-first traversal technique in which you always visit the root node before visiting left and right subtrees. So, in the previous lecture, we learned about tree traversal techniques, that is, going through all the nodes of a tree such that each node is visited exactly once, that is traversal. In traversal, we learned there is something called DFT, depth first traversal. And in depth first traversal, there are three different techniques. First one is called pre-order traversal. Second one is called in-order traversal. And third one is called post-order traversal. What are pre-order, in-order and post-order? So in all these, keep one thing in mind. This is a general rule that whenever you are doing any sort of tree traversal, always go through the left subtree before going through right subtree. So whenever you want to traverse a tree, go to the left subtree, and only after completing left subtree, go to the right subtree. So this is general, whether it be pre-order, in-order or post-order. Now what differentiate between these three? First of all, what does pre mean? Pre means something that happened before. That is what you call as pre. What is post? Post means after. And in means rightly in order. So this is on the basis of position of root in your traversal. So if you want to go to the root before left and right subtrees, then you call it as pre-order. That is, before visiting left and right subtree, you want to visit root. If you want to visit rightly in order, then you visit root in between left and right subtrees. And what about post order? In post order, you visit the root after visiting left and right subtrees. So this is the difference. So in this lecture, we'll only be looking into pre-order traversal. We'll go in depth in what is pre-order traversal, what is the algorithm, dry run, everything. So let us start with pre-order traversal. It will be easier to understand through an example. So we'll start with an example. So we already told the order is root, then left subtree, and then the right subtree. This is the general order to be followed for pre-order traversal. Let our tree be this. A is the root. A has two children, B and C. B has another two children, D and E. And C has, let us say, only one child. Only left child is missing. Only right child is there for D. It is F. Let us see how to do pre-order traversal on this tree. So the general rule is root, after root left subtree, then the right subtree. So let us start. Root is A. After visiting A, we have to go to left subtree and then the right subtree. So can I write A, then B, then C? Is this right? No, it is not right. What is not right here? First, you have to visit the root. So A is right. Then you have to go to left and right. So it should be B and C. No, it should not be, because it's not simply about visiting left and right nodes. This is wrong. You have to visit the complete left subtree. After that only you can visit right subtree. This is the rule for pre-order traversal. So now you visited root, which is A. You have to go to the left subtree. So this is what you have to visit. In the left subtree, again you apply the same rule. Root, which is B now, then left subtree, then the right subtree. So here, what is the root? B. So you can visit B, which is the root. So I have visited B. After B, what do I have to do? I have to go to the left subtree of B. So in left subtree, there is only one node. So I can directly write D. So D is also visited. After this, I have to go to the right subtree. That is right subtree of B. So it is E. So I'll write E. So here E is only one node. So I don't have to again do root left and right. So I can simply visit E. So complete left subtree of A is completed. A, B, D and E are visited. So I can move to the right subtree. In the right subtree, I'll again do root, left and right. So root is C. I visited C. After visiting C, I have to go to the left subtree of C, which is empty because C doesn't have a left child. Then I can go to the right subtree of C. So it is having only one child, which is F. So I'll visit F. So I have visited F. So this is the pre-order traversal A, B, D, E, C, F. So first I'll go to A, then B, then D, E, C and F. This is the order of traversal in pre-order traversal. So if you are finding this difficult, that is if you think it's difficult to do this pre-order traversal, I'll tell you a technique. So it is logical, but it is easier with another technique which I'll tell you. So it's important that you logically understand what is pre-order and how to do it. What I'm trying to tell you is a hack if you want to simply know what is the pre-order of a tree. So let us take the same tree and let us see how to derive this order with a simple technique. So the technique is this. You start from A and you simply go through the tree like this. Whichever be the node that you see, simply write it down. It will be pre-order traversal. This is the technique. So let us try this once. I'll start from A. So I'll write A. I'm going down. I saw B. So I'll write B. Again, I'm going down. I saw D. So I'll write D. Again, I'll visit this. B is already visited. I reached E. So I'll write E. Again, I'm coming up. B is already visited. A is already visited. C is a new one. Again, I'm coming down. F is a new one. I'll write F. Again, F is already visited. C is already visited. A is already visited. Traversal completed. See the order? It matched exactly with the pre-order traversal. So this is a hack if you want to simply understand pre-order traversal of a tree. Simply draw a line just very close to the tree. Whichever be the node you are seeing, simply write it down. It will be pre-order traversal. So this is the technique for finding pre-order traversal. So now you know what is logically pre-order traversal. You know how to find pre-order traversal directly if you see a tree. So see, this tree is very simple, so it will be easier to find pre-order traversal. But if you are given a very complex tree, this hack would really help because it might be difficult to see root, left, right like this. So this is about pre-order traversal. What we'll do now, we'll see what is a pseudocode, how to write a function which will find pre-order of a tree. And then let us see how that function works. Okay, so let us understand this first. In order to do pre-order traversal, logically, what is the rule? You have to first go to the root, then the left subtree, then the right subtree. This is the rule I have to follow. So how can I convert this into a function? How can I write a function which will print the pre-order traversal of any tree? So let us try doing this. So this is my function, pre-order of node. So we'll start this function from the root of the node. So what are the steps that are required in this function? Because it is pre-order, first I'll print the node, print the root node. So here we are starting from node. So I'll print node. So this is step 1. Step 1 is print node. So after printing node, what is step 2? I have to go to the left subtree. So I'll call the same function preorder of the left subtree. What is left subtree? It is node pointing left. And then I have to go to the right subtree. So for that, I'll again call the function preorder of node pointing right. This is how I do pre-order traversal. But something is missing. What is missing? When to stop this? That is, whenever I see a node, I'll print that node, okay. Then I'll go to the left subtree, then I'll go to the right subtree. So this is recursive function, that is this function is calling the same function again. So where do I go and stop? This is what I have to decide now. For that, I have to find a rule. How do I stop? Whenever I am in a tree, let us say this is the tree A, B, C, D, E and F. So we are taking the same tree that we took previously. How do I know that I have to stop? I should stop whenever I reach a place where there is no node or the node is null. That is when I have to stop. So what do I write as the exit condition? Base condition is if node is null. If my node is null, what do? I will return. I have to return. So this is the base condition. Whenever node is null, I should return from here. If the node is not null, then only I should do all these things. So whenever the node is null, I should return. Let us try running with this function and let us see whether we are able to find the pre-order traversal. If I run this function, how will it work? First, I'll start from A. From A, I'll start running. So what do I have to do? I have to first print A. First I'll print A. So that is done. Then I'll call preorder of node pointing left. That is, I'll call preorder on this part. And then I have to call preorder on node pointing right. Then I have to call on this part. This is how the function works. Then when it is called for this part, again the same function is called, node will be printed. Then preorder for D will be called, for E will be called. This is how this function looks like. So we'll do a dry run after this. First, let us analyze the function and understand. So this you already understood, that preorder function, first you have to print the node, that is the root node. After root, you will go to the left and then you will go to the right. So it's very simple function. Let us understand time and space complexities. Then we'll do a dry run of this. Then you will clearly understand. This is return. So what is the time complexity? Time complexity is this function is going to print all the nodes. That is, it is going to go through all the nodes one time, which means if you have n nodes, time complexity is order of n. And what is the space complexity? Space complexity, you would think this is not taking any space because you don't see any new space initialization, which would mean space complexity should be order of 1, constant. But this is wrong. It is not constant because you are using recursion here. Whenever you use recursion, what happens is recursive stack will be called. So whenever recursion stack is called, the stack will take up some space. So this space will add to space complexity. So let us understand this first. So whenever you are calling this function, I'll draw a small tree here so that we can analyze this. A, B, C, D, E, and F. So this is the same tree that we previously analyzed. Let me draw this neatly. D, E, and F. So if this is the tree, let us see how this function would run on this tree. So this is return. So how will this function run? So this is my recursive stack. In the recursive stack, first I'll go to A node. So in A node, I'll call preorder of A. Okay, I call preorder of A. So this is there in the stack. So when I call preorder of A, it will first do step 1. I'll call this as step 1. This is step 2. This is step 3 and this is step 4. So in step 1, it is checking whether the node is null. A is not null, which means step 1 is crossed. Then step 2 is print node, which means I'll print A. I printed A. Then step 3. Step 3 is preorder of node pointing left. So I reached step 3 here. So in step 3, I'm calling preorder of node pointing left, which means I have to call preorder of what is node pointing left? B. B is node pointing left. So I inserted B into stack. That is preorder of B. It is inserted into stack. So when it is inserted into stack, next step to be executed here is line number 4. And in B, I am executing line number 1. So line number 1 is whether B is null or not. So B is not null. B is an existing node. So I'll go to the line number 2, which is print node. I printed B. After printing B, I have to go to node pointing left. So left of B is D. So I'll call P of D. When I call P of D, what happens to P of B? P of B, already it is in line number 3, which is node pointing left. Next line to be executed is node pointing right. So fourth line is to be executed in B. So P of D is newly inserted. Now I'll call P of D. P of D will do whether it is null. D is not null. D is an existing node. D is the. Then I'll print node. I'll print D. Then I call preorder of node pointing left. So D's left child is null. So this is preorder of a null node. When I call for null node, what happens next? So again, here I have to run fourth line. When I call preorder of a null node, this line when I'm executing, in first line itself it says if it is null, return. So whenever I return, this will be pushed out from the stack. So it is popped from the stack. After popping from the stack, I'll again take D. For D, I have to run line number 4. Line number 4 says node pointing right. So that's again P of null because D's right child is also null. So again null is return, which means this is also popped out. This is completed now. All the 4 lines are done for P of D. So preorder of D is completed. Now I reached preorder of B. Preorder of B says preorder of B is fourth line is remaining, which means node pointing right. What is right node of B? Right node of B is E. So I have to call preorder of E. Preorder of E when it runs. So here all the 4 are done. And when I called preorder of E, so here I'll write 5, which means all 4 are done. And for preorder of E, it checks whether E is null. E is not null, which means it calls preorder of no print of node, which means E is printed. After printing E, it will call pre of node pointing left, which means pre of null node, because left child of E is null. Again, it will be popped off. Again, you will come back to E's fourth line, which is right child of E. You will again call for right child of E. So I am doing this in order to make you understand how this stack is getting filled and memory is getting used. Okay. So you need to understand how memory is getting used in recursive algorithm. So now this will again be popped off. Then E's fourth line is also done. So E will also be popped off. You will come back to B. You will see B is also done. So B will be popped off. You reached A. A's fourth line says preorder of node pointing right. So for A, you will push P of C. What does P of C says? Node is not null. So next step is print node. Print node says you have to print C. After printing C, what do? You will go to line number 3 of P of C. Line number 3 says node pointing left. C doesn't have a left child, which means this is null. So preorder of null. Preorder of null means you have to pop it off. Again, fourth line says preorder of C's fourth line says node pointing right. So C's right child is F, that is preorder of F. After calling preorder of F, you will print node F. Then you will see node pointing left, which is null. You will pop off. Node pointing right, that's also null. You will pop off. Then you will come back to F. F will be popped off. After popping off F, C will be popped off, and finally you will reach A. A will also be popped off. So this is how you run the whole algorithm. That was a dry run. So I wanted to show you how that stack is getting filled when the algorithm is run. So that stack consumes space. What is the maximum space that stack can consume? So ideally, if I am considering a balanced tree, if it is a very balanced tree, then the maximum height possible, that will be the maximum size of the stack. So whatever be the maximum size of height of the tree, that is what can maximum be the number of entries in the stack at any single point of time, because after that it will be popped off. So height of the tree can be maximum order of log n if it is a balanced tree. But we are not considering simply balanced trees. All trees are being considered. So it can so happen, you can have a tree like this. It is having continuous left child, left child, left child, and it is just growing on one side. So this is called a skewed tree. In this case, if you have n nodes, all n nodes can be left child to each other, left child of next nodes. And in this case, your height will be again n. So worst case space complexity is order of n, because in case of skewed trees, your recursion stack may go up to n. So in that case, space complexity is order of n. Time complexity, we already discussed, it is order of n. Because why is time complexity order of n? Because you are visiting all the n nodes anyway. That is what traversal is about. You have to go through all the n nodes. So time complexity is always order of n. Space complexity also you understood, it is order of n. If it is balanced, it will decrease. That we'll understand when we go to the balanced trees.